is we're going to do this 2D particles in space. And what's different about this is from last lecture is nothing, except for that today I'm going to do the MATLAB that I intended to do at the end of last class. And then we're going to go on to try to catch up a little bit with where we're supposed to be on the syllabus and talk about pulleys. And I will try to explain as we go a little bit the logic of the organization. Why are we going from something harder to something easier? And there's a reason for this madness. Okay, so I'm going to start right in. I want you to remember where we are. We have these two particles in space. Remember, what is a particle? It's an infinitesimal dot, like the sun or the earth. Okay, what's a particle? We don't really mean an infinitesimal dot. We just mean a thing about which we ignore everything but its position. Doesn't mean it doesn't have extent. It means we just don't pay attention to its extent. We don't pay attention to motion relative to the center of mass. So we've got these two particles, and they're in space, and they might have forces on them, like the hand of God pushing them around, or they might have attraction to each other, or repulsion from each other, or drag in the atmosphere and things like that. And we want to figure out how they move around. How do they move around? Each particle obeys F equals ma. So we just write F equals ma for each particle and integrate forward in time. What does that integrate forward in time mean? It means knowing the current velocity and position, we can calculate the acceleration. Those are what is called the equations of motion. And knowing the velocity, we can calculate the velocity, which is the change of position. And those two things tell us how the particle advances, both how its position advances and its velocity advances. And same with the other particle. And so all we do is F equals ma for each particle. And that's what goes back to that quote of Laplace that I told you before, where he said that if you tell me where everything is and how fast it's going, I will tell you the future of the universe. By which he meant he thought he lived in a Newtonian world where the equations of mechanics were the correct equations of everything, and therefore he could predict the future from that. We pause for a little fire break here. Ow. Okay, so now we'd like to do that Laplace thing. Our universe is going to be simple, just two particles like the Earth and the Moon. We like to see how they move around. How are we going to do that? Integrate F equals ma. Could we do that with pencil and paper? I guess that one or two of you could do that now. If I took a lecture, I could show you how to do the two-particle system with pencil and paper. It's not that simple. It takes a funny change of coordinates to figure out that the inverse square law gives you ellipses. Has anybody been through that calculation? Where was that? Okay. So what you did the 1 over r, change of variables and so on. Okay. So it's a tricky little calculation. It's not something that you would think of easily on your own. It took Newton a long time to figure it out. We're not going to do that in this class. We're just going to jump to the computer and not pay attention to whether we could do it in pencil and paper or not. Okay. So how does it go? I've got here a collection of files in a folder. So now remember last time, or previously, I was bunching a bunch of MATLAB functions into one text file. But I could put each MATLAB function into a different text file. So I've started this new problem by doing an old problem and putting the different functions in different text files. Remember, bit by bit, we're trying to work our way up into understanding OD 45. So now I've got two different right-hand sides in case I want to do two different problems. I've got two different solvers, the midpoint solver, the Euler solver, and I've got my driving function here, which runs the show. So let's just start out with, say, the solver part. Here's supposedly Euler's method. And this, remember, I said this one function, it used to be a collection of text at the bottom of a text file. Now I have it as a separate text file. Is all of Math 293. And what I've got here is the midpoint method. So I think I'll drop back to doing just the Euler method. So I'm going to calculate z dot, and I'll calculate it like this. So there's going to be no temps. I called this Euler method, and I actually started with the midpoint file, so I'll modify it back to Euler method. I've got z dot equals, and I have this line here which I don't need this temp business. In fact, I can just call this the Z new, and I can call this H, and then I've got my whole thing, and I just get rid of all these lines because I'm not doing the midpoint, I'm just doing Euler's method. Okay, so Euler's method is all packed into basically this one line of code, which I think is the line you had to fill in the exam 2 nights ago. I've done something a little funny here, though. So the way we did things before was with this line of code. We calculated the right-hand side. We called that z dot, and then we moved forward in time by taking the rate of change of variables times the step size, add that to the previous value, and that gives you the new value. This is how we predict the future. There's 2 parts to the crystal ball. One is the method of integration, and one is the rules of the world. Here's the method of integration, Euler's method. Okay, so the way we did this before was like so. We calculate the equations of motion in a file called right-hand side, or right-hand side 1, and then we call that z dot. Now I'm going to do something different, which is I'm going to add an argument to this function, which is the name of the right-hand side variable, function. This is all going to be posted online, so just unless you need to take notes to make yourself focus, you can just pay attention, and then I'll post it. And now I use this funny command here, which is not my command, it's a MATLAB command. And you don't pronounce this feval, you pronounce it feval, as in function evaluation. And this is a MATLAB function which does the following thing. It takes the first variable, it hopes that it's a text string, and that somebody, when they passed in this first variable, it's not a number but a text string, and it's the name of some function that MATLAB can find. And then it does function evaluation, which means it evaluates that function with these arguments. So long as I have made sure when I called this function that the text string inside this variable was the letters RHS1, then this line of code does exactly the same as this line of code. Now, if the text string here had been called RHS2, then this line of code would have been like this line of code, but I changed that to a 2. Okay, should I say that whole thing again? You want to ask me questions about it, or should I go on? Yes? Why would I do it like this is because here I have all of Math 293. This is a general purpose solver of differential equations. And rather than have to have inside my general purpose solver the name of the differential equation I want to solve, I want to be able to call this general solver and say, solve this equation, and I give it the name of the equation I want to solve, which means it's the name of a file where the equation is going to be, as well as the times I want to solve it and the initial conditions and the parameters. So this makes this, this function, this thing I'll call solve ODE, which I think I actually called this solve Euler, so I'll just make it consistent. It's easy to get confused if this word here is not the same as the file name. You can get confused and not know which one MATLAB's going to use. I want this to be a general purpose solver. That's why I do this. So I'm going to take this block of code and I'm going to put it away and never have to look at it again. Whenever I want to use it, I tell it what's the equations I want to solve, the time span, and the z0. That's why I'd want to do it. Does that address your question? Yes? In line 19, should z.temp be z dot? Yes. Any other questions about this block of code? Okay, so we replace all of Math 293 with this block of code. It's not a very good replacement because I'm using Euler method instead of midpoint method, but I could have another block of code which has midpoint method. In fact, I do have that block of code. That was the one I started with. I actually went backwards here. Here's the midpoint method, and that's the whole thing done correctly. And now that we know what to do with that feval thing, I can just delete this line of code. And I can delete this line of code to make it look a little simpler. And now we have this funny thing. It looks confusing. Feval, evaluate the differential equation, whatever it is, with t and z and p. And then we do this half step and another half step and so on. So now I've got these two solvers. This one I should also properly name. Let's see, I called the file solve midpoint, so I should call this, so I don't get confused, solve midpoint. I think the name MATLAB tends to use is not the name that's here, but the name of the file. But nonetheless, just have it consistent so you don't mess around with it. Okay, so now I've got my, this is now Math 293. Last time I did all of Math 293, I got a grade of C because I didn't solve them very well. Now I get a grade of B. I solve it much better. Now if I want a grade of A, I'll switch over to ODE 4.5, which is even fancier than this, but let's skip, we're going to get to there next time. We're working our way there. Okay, now what about the differential equations? So I've got differential equations. Here I've got right-hand side 1. RHS1, RHS1. These are differential equations. Now these are the equations of motion for the Earth and the Moon. Okay, so now where that last code was all of 293, here's a big chunk of dynamics. This is what you're supposed to be able to do, is write this code, write the equations of motion. Of course, you're supposed to know something about the solutions too, but the main thing in dynamics is just these two lines of code. The rate of change of velocity of particle A is the force on particle A from B divided by the mass of particle A. And the acceleration of particle B is the force on particle B divided by the mass of particle B. What is that force? Well, the force on particle A, if we're doing the Earth and the Moon, is the universal law of gravitation. G times mass times mass. Sometimes they write this in physics as big M, little m, but who knows which one's bigger, which one's littler, divided by the distance squared, times the unit vector in the right direction, which is RAB divided by the distance. What's RAB? It's the position of one minus the position of the other. What's the distance? It's the norm of that vector, or you could think of that as the dot product of that vector with itself. And if I want to do this and have it right, it should be the square root of the dot product of the vector with itself. That's what the norm means. So going down to this code from the beginning, this is a differential equation for the Earth and the Moon. I bring in a long list of numbers. How long is this list of numbers? Think to yourself for 10 seconds. I'm not going to quiz you, but just 10 seconds, think about it. Okay, I stop you at 8 seconds. 1 second for each term is 8 terms. So the first two are the positions of mass A. The second two are positions of mass B. Then we get the velocities of mass A and the velocities of mass B. Given all those things, we want to predict the future, the rates of change of all those things. The rates of change of the positions or the velocities, the rates of change of the, and that's, so 4 of our differential equations are just trivial like that. And then we need to get the rates of change of the velocities. Those are the accelerations. Those come from Newton's laws, which we've just worked out right here. So here's all of Newton's laws. And now we've got the rate of change. So we've got the differential equations for this Earth and the Moon going around each other, or the Moon and the Earth and the Sun, or whatever it is. Okay, any questions about this? If you want to say what's the, the essence of this class, the thing I would hope you would be able to do competently 2-4 years from now, even if you're getting a C in the class, is like this much of this code. You should just, this should be in your blood, if not at this point, shortly, in some deep way that it sort of sticks with you for the rest of your life. Any issues about that? Okay, will somebody ask a question just to help? Just ask the stupidest question you can possibly ask, just to sort of break people's brains up so they can think in a different way. Okay, we have a competition here. Who can ask the stupidest question? Yes?
What are the P dots you have before MA and MB?
That is a really stupid question. I told you 10 times already. Those are the parameters that get passed in.
But why do you have the P dot instead of just the MA and MB?
That is even dumber than the last one. Because It's so ugly to write a long list of variables here. I want to store them all in one variable. So I want to have an array of parameters, and MATLAB allows you to label the array with this dot syntax. So p.ma means ma, p.mb equals mb, p.g means g. And it's not because I want it inside this program to make sense. It's because I want to pass it in easily. If I wanted this program to be more readable, I could have up here put a bunch of lines like this. G equals p.g, ma equals p.ma, and so on. And then I would have made the whole rest of this program more readable, but I have to add all those lines of code. Okay, now can anybody ask a stupider question than that? Yes? What was the question?
Why do you have all the percent signs at the bottom?
Why do I have all the... That is a really stupid question. Because this is left over from when this was part of the other text file, and I was trying to isolate the different functions in the text file with something for my eyes to see where one function started and the other stopped. Any other dumb questions? Yes? Right, so the notation we're going to use is a little tricky here because I'd like you to use good vector notation on paper, but in MATLAB we're always dealing with lists of numbers and we don't have we just have text strings. But this is supposed to be reminiscent of the vector equation, and you're supposed to think in your head when you see this, R with an arrow on top, subscript AB. And that means from A to B, and that's the opposite of R with an arrow on the top, subscript B/A, which means the position of B with respect to A. So say you're B and I'm A. AB is that arrow, and B/A is also that arrow. That's where you are with respect to me. It's the same as where the arrow from me to you. Does that address your question? Any others? That wasn't the stupidest question. So, but yes? Okay, that wasn't a stupid question. That was a stupid line of MATLAB code. Okay. Any others? I like this scheme. I haven't done this before. Because, you know, what they teach you is, in teaching school, is you're supposed to treat every question with respect. And so going the opposite maybe works every now and then. Okay. Yes? RAB and RAB. So one way to think about the magnitude of a vector is the dot product with itself, square root. Any others? I ran out of change, so I can't pay you for that. And that. Okay, so now we've got the equations of motion. Now we go back to making the whole thing work. So now this is like just all the bookkeeping to make all that stuff work. So this is really, there's nothing interesting in this big mess of code. It's just setting things up. So this is where we're going to run things. It's going to be called trajectory. I think I call it trajectory 2, so I better make that consistent. CTAM lectures from 2/28/2013. Clear all. Here's the start time. Here's our step size. Here's the last time. Here's the number of times. Here's a list of all the times, which comes from putting all those things together. We've got the initial position of block A, the initial position of block B, the initial velocity of A, the initial velocity of B. We put those all together into some big initial condition vector. We assign all our parameters with these P's because we want to pass it in with a single letter rather than a long list of things which we might get confused about. Right? Who asked a question about the P? Are you happy with that answer? Then we want to solve these equations, and now we say we're going to solve it using our method of choice. And we could put here midpoint, Euler, ODE 4/5, any solution we have, and then we say what differential equation. We tell it what differential equation to solve, and we tell it what time, what initial conditions, and what parameters. After it solved it, these functions don't really know the meanings of z. It's just lists of numbers. Well, actually, the inside of that right-hand side file, we gave meanings to the variables for a while. After we solve it, then we unpack that list of z's and say, oh, yeah, the first two were the position of x. The second two were the position of, at first mass. The second two were the position of the second mass, and x and y coordinates. Then we plot, and now we do a cross plot of the positions of particle B and particle A. B we draw with the line, red we draw with the dotted red line, and then we make this cross plot with these initial conditions, and I hate to say it, but I cheated a little bit and did ones that I thought were cute. And then we run this thing and we get this pair of ellipses. Meanwhile, I found this good command, which is good for lecture, is shg, show graph, so I don't have to go fishing around for the graph afterwards. When I run this thing, the last thing it does is it put the graphic window on top. Now, where did we stop? Where did we end? Well, we started over here at +3 and -3. One was going up, one was going down. They weren't going that fast, so they went in and they sort of fell into each other. What if I put 1, -1, and 1, and done the same thing? Then they would do something a little bit different. Whoa. So what happened there? So now we don't know. Did we make a numerical error? Or are these things trying to fly into outer space? We don't know, right? So we can back off and say, what happened? Let's just go for a little bit of time and see whether that was meant to do that. Let's see. They're flying towards each other for a while. Let's do it for a little bit longer in time. They're flying towards each other. What's going to be the problem, do you think? They're flying towards each other, and they get very close. Now, when they get very close, what should happen? Well, according to the proper solution with pencil and paper, according to Newton, all the trajectories are either hyperbolas, parabolas, or ellipses. And this numerical solution is giving something that does not look like any of those. Why is it messing up so badly? Here it's doing this nice arc, and then it's going flying out crazy like that. It's because there's a lot of fast stuff happening in there, and I'm not integrating very accurately. So if I integrate more accurately, it should do better, I would think. So that was an artifact of bad numerical solution, and now they're falling in and trying to do this nice thing like that. Now, if I launch them a little faster, 1 in these crazy units, what happens? Now they go off, and they go out. That's escape velocity. They're going out into outer space. What if I only make one of these velocities 0? What's going to happen? Run it for a while. Now, what do you see what's happening there? They start here, start here. This one's launching down. This one has no initial speed. It starts getting attracted to this one. But as usual, when you chase after things, they run away. It runs away. This thing is running down this way. This one keeps chasing it. This one's being slowed down by that one. What happens after a long time? Let's run this for a longer time and see what happens. It says, you're making me work too hard. Okay, now they go far away. They jump back close together. They run far away. Now, is this way wrong or not? Actually, I don't know. Because what part of the confusion is, remember we said it always is ellipses or parabolas or hyperbolas? It's always that relative to the center of mass. But if the center of mass is moving, it makes a complicated curlicue. So, for example, let's go back and do a problem that we know has a nice, simpler solution. So let's go back here. Let's do -1 and +1. -1 and +1, was that falling into each other or not? I forget now. That was running away. That was past escape velocity. Let's go 0.5 and -0.5. Is that escape velocity more or less? Oh, that's a beautiful one. Okay, so -5 and 0.5, the numbers happen to be right for circular orbit. So what if I change that into a 1 and a 0? It's kind of the same problem, only displaced in velocity. So this is actually the same solution we should get, but it doesn't look the same because it's translating in time. So we get this thing that looks like a cycloid. Actually, does anybody, I happen to pick one so that this is exactly a cycloid. That's just the numbers worked out. Does anyone know what a cycloid is? If you turn this 90 degrees, look out on the side, it's the path of a piece of rock that's stuck in the tread of your tire as your car rolls along. So this is a superposition of circular motion and translational motion. Anyway, you can play with this all day, years, centuries, these equations and how they work out. Thousands of people have spent thousands of years just looking at all these solutions. Yes?
You have to transpose the initial condition.
Why do I do that? Because I made a pedagogical error at the beginning of the semester about how to teach this stuff. That's why I have to do it. So you do not have to do it. All the transposes I've done all semester I could have not done, and I could have left everything row vectors. I chose to make everything column vectors to line you up for ODE 4.5, which is the next thing I'm going to do when I do these differential equation solutions. So you'd be used to it, but I shouldn't have done that. I should have got you used to this whole way of doing things without the transpose, so you wouldn't be confused about that, and then thrown in the transpose as a screwball at the end. So the reason I did it is because I made a pedagogical mistake. Does that address your question?
Yeah, so I guess ODE 45 has to have the transpose.
ODE 45 demands to work with column vectors, even though the output of it is a whole list of row vectors. Okay, so I'm going to give you this package. You can use it to play with. I would like it if you would be able to erase every file and write them all yourselves. Then, if you can't, surely you'll have mistakes. I would like it if you got help from MATLAB help rather than from looking at my samples. So you go through this debugging process. The main thing, if you want to say, what are the important things to learn in a class like this? Okay, first you're supposed to learn dynamics, then the tools. MATLAB happens to be a useful tool, probably in the long run. All of you are going to use MATLAB here and there. Only some of you are going to use dynamics. But really what's the important tool? You know, why do they say Cornell engineers are great? Is problem solving. And what do they mean by problem solving? It's the ability to look at a problem and solve it. What does solving it mean? It means trying things out and debugging them and fixing them. So this process of getting stuck in MATLAB and then unstuck by reading help files, trying things, doing experiments, commenting, uncommenting, trying this variable, setting the time to small, so on, that is the most important thing you have to learn in this class and every other class. So when you go to do this thing yourself and you're frustrated, that is your biggest learning opportunity. And I'm not like joking and just being pedantic and preachy. It's really true. That's the most important thing, is when you're stuck, working your way out and figuring it out. And computer programming is a great place to do that because it's an auto-tutor. You don't need a human being there saying, no, that doesn't work. It just goes, syntax error, file 326 not found, or whatever. You just have this automatic teacher helping you do this debugging process. Okay, any questions? How many people believe that speech I just gave about learning to debug is really the most important thing? Okay, come on, go for it. This is it. Okay. Now we're going to go on. New topic. Totally new topic. Ready? Computer goes away. Whole new thing. Okay. Okay, the computer doesn't go that far away because I'm going to give you a quiz. I'll do it over here so I can, I hope. Okay, we're going to go to the word of pulleys. And I'm just going to start right in with a quiz. And then I'll talk about what we're talking about and how to deal with these things. So I've got pulleys are amplifiers, mechanical amplifiers. And you want to understand pulleys as mechanical amplifiers. So I imagine a situation like this where I have a pulley and I'm trying to use it to pull something, and I pull on it something like this, and I pull with some force F, and I have some force here, M. And that's a pulley system. And I'm going to call this point here A. Now I have another pulley system, and I'm going to use pulleys again to help me make things amplified. And I have walls all over the place, but I don't necessarily use these walls. And I put over here a force here, and I'm going to call this B, and I'm going to put a mass over here, M. And I'm going to follow the Laurie Anderson song, which I tried to play for you, but the sound system wasn't good. Remember a few weeks ago. But the words of the song were, let x equals x. So, of course, let f equals m, f, and m equals m. And the question we want to ask is, in this situation, what is the ratio of the acceleration of B to the acceleration of A? Okay, now I'm going to give you like 2 minutes to work on this. Talk to your friends. And I'm going to give you a bunch of choices. Actually, I'm not going to give you a bunch of choices. I'm going to take numbers, and then in the end, I'm going to do an honor system. I don't know how I'm going to do it. A is connected to the pulley center here. This is connected to the pulley center here. This is connected like so. Does that address your question? Who asked the question? Are you happy with it or no? Yes? The pulley does not have mass. Or, if to say it more properly, it's the mass. We neglect the mass of the pulley. It's not that it has no mass. It's that we think that the difference between the answer with the mass it has and the answer with taking the mass to be 0 to be negligibly small. Put up here the first 5 answers that you give me, and then you guys have to pick between them. Okay. Or maybe I'll take the first 4 answers that you guys give me, and then we'll do none of above. So you can't play psychological war with me, because it's going to be you who's doing it. Okay, somebody raise their hand and tell me a candidate answer. Yes? 2 to 1. Anybody else have an answer? Yes? 4 to 1. Anybody else have an answer? Yes? 16. Anybody else have an answer? Yes? 1/2. 1/2. Okay? Now, you guys get to vote. Okay, do you want to see the votes as they go up, or do you want to see them after you make them? You want to do social dynamics along with the dynamics. Then we got to write differential equations for how the lines go up, because one goes up, and then other people think that's a good idea. Then they see the smirk on my face, then it goes down, and then... Okay, B's looking good here. You think B is good? Huh? You think B is good, do you? Oh, you do you? What about C? What about D? C? C's looking really good. C's looking really good. Okay. Now, I'm a very honest person. The fact of the matter is I really am an honest person, but I'm incredibly good at lying. So do you think you could ask me questions? I think I could. You'll never know what I think. Okay. Now this is obviously a ridiculous answer, right? but it's the right one. What? How could, look, this innocent problem with just a piece of string and a mass, where could 16 possibly come from? How could that little innocent problem have 16 hidden inside it? Well, I'll tell you how. 2 times 2, what's that? It's sort of like the 2 plus 2 problem. We can do that one. And then if you do 2 times 2, you can do that one. It's the same problem again. That's easy when they give the same problem twice. 4. And then if you take 4 times 4, 16. And that's what's hidden inside there is 16. So I'd like to get you some intuition for this problem. And for this purpose, I need 2 volunteers. 2 volunteers. There's one. You got to come down here. Do you want to be a mass, a wall, or a force?
I'll be a force.
You'll be a force. Okay. So forces are on that side.
All right.
I need a mass and a wall. Please. Okay, go ahead. Okay, I think I'll be the third volunteer.
Okay.
Okay, so you are a wall, and we're going to do problem 1 over here.
Okay.
So you're standing here, and you're a wall.
Cool.
Okay, now you are a force.
Yep.
And you guys stand close to each other. So there's no, we think of it as a 1D problem. Okay, now wall, you stand still. You're not allowed to move. Lean against the desk to make it unambiguous. Okay, now you force are going to pull me. And when you pull me, I come along. Now how fast do I go relative to you?
Slower.
About how much slower?
Maybe half slow.
Maybe half as much, right? There's 2 pieces of string. I go half as fast. Now you're pulling with a force F. What's the force that's pulling on me?
2F.
Right, because I've got a string here. I got a frictionless pulley over here, and you're pulling on it. And I've got tension here, so you pull. Go ahead, pull. Force of 2 is acting on me. So my acceleration is 2F divided by m. But look what he's doing compared to me, twice as much. That's 4, right? His acceleration, drop that. His acceleration now is F divided by m. And in this experiment here, hold on. Now pull. Woo! You're not pulling fast enough. Sorry, I was too excited there. His acceleration is 4 times as big because he's getting, his force is getting through twice to me, and then his motion is another factor of 2. So his acceleration is 4F over m. That's problem 1. So there's a 2 times 2. 2, because I get twice the tension. 2, because he goes twice as fast as I do, and twice acceleration. Okay, now let's do the second problem. In the second problem, what's the difference? Well, what did we just do? We just did the second problem, right? Now we want to do the first problem. Okay, you go over there. You're the wall. You're the pulley. And let's see, you don't have to lick your hands and do all that stuff. I'll spare you my spit.
Thanks.
You're the pulley. And now you're going to pull. Now you don't move. Lean against this desk so it's unambiguous.
Yep.
Okay, now I'll stand out of the way. Now you're going to pull. Look how fast I move compared to him. I go twice as far as he goes. Now he's pulling with some force F. What's the force that I'm getting over here? There's a tension here and a tension here, and these 2 tensions add up to F, so I'm only getting F over 2. So I'm only going with an acceleration of F over 2m, half what I would have got if he pulled on me directly, and he's only going half the acceleration that I'm going. So there's a factor of 4. And 4 times 4 is 16. Okay, so we'd like to be able, before you guys sit down to take questions, we'd like to be able to calculate this with confidence, but you'd also like to build some intuition for it. It's an amazing fact, I think psychological fact, that hidden in these two things, which if you just are sloppy, they look like the same thing to you. And they're not just not the same thing. They're different by a factor of 16 in some ways. It's just sort of funny that we are so bad, despite the fact that our first lesson on pulleys was when we were 3rd grade or something. The teacher brought in a little plastic kit. So you've been through this for at least 10 years. That despite that, we're so bad. So you're not the only ones. Like when I go to write this on the blackboard, I have to stop and think. And if I'm not careful, I'll just draw the same picture twice. And I feel, oh, that's not quite right. Or even when I was doing this demo, I thought I was doing A, but I was actually doing B. It wasn't until I was halfway through that I knew which one I was doing. So you're not alone in being confused about this. But it's sort of, I don't know, just a funny thing that our intuitions are so bad about these things, even though you can do the experiment so easily. So if you want to do this at home alone, take any old string you find, and you can do the experiment yourself. You have a wall. You have a pulley. You have a mass. So you can do the various things and play with it and try and build up some intuition for it. Okay, so any questions before they sit down about the intuition for this or how it works? Yes? If we draw a free body diagram of A, so here's A with a little string coming off. We cut it and fool it into thinking a force is applied, which it was. And we cut it over here and we fool it into thinking something's over here. There'd be a tension. We don't know what that tension is yet. The string has negligible mass. The sum of the forces is the mass times the acceleration. It has negligible mass. The sum of forces is 0. So even though this thing is moving, we use statics because the mass was negligible. So this tension is equal to that force. Does that address your question?
I'm not sure how you get
Where did that factor of 2 come from? The factor of 2 in the pulley came from a couple of things. One is that there's this tension over here. I'll call this T2 to distinguish it from T1. And then there's a tension over here, which was T. This tension is equal to that tension. Now it takes some reasoning to get that this tension is equal to that tension. We had to separately draw a free body diagram of the pulley, neglect the mass of the pulley, assume that it's round and frictionless, take sum of moments about the center. Then when we take sum of moments, it's got this radius and that radius. Since the radius is canceled, so this tension has to equal that tension. The net result of a sort of several lines of mechanics reasoning is that a frictionless, round, massless pulley has equal tensions on both sides. Then we get that these tensions have to be half of this one if we neglect the mass of this. Does that address your question? And then the same thing happened with this free body diagram. So this is part, I'll call this T3, T3, T4, and these tensions have to be half of that one. So that's part of the reasoning in these problems. Any other questions? Okay, so now before I get into the reasoning here in detail, let me give you a little philosophy. Okay, you guys are out of here. Thank you very much. Let's have a big hand for this guy and that guy. That wasn't such a big hand. Okay. The basic, let me tell you oh, that's a good one. I'll get there yet. So our basic pulley solutions is to draw free body diagrams, two, use linear momentum balance, and three, use geometry kinematics. And in terms of mechanics problems having three pillars in them, laws of mechanics, which is here, and geometry, which is here, and material properties. The material properties are so simple in this problem, inextensible strings, you don't really see them in the equations. Why are these simple problems being done now in this class when in principle you did them, I don't know, starting in third grade? And why do I consider this problem harder in some ways than what we've done so far? Well, one thing is, as I showed you, our intuitions are bad, so it deserves like stopping and thinking carefully. All but 4 people in the class or something like that. But another is that there's a conceptually hard thing in this problem which we're going to be stuck with for most of the rest of the semester, which is that this is a problem where there are constraints. And by constraint, we mean that there's some geometric restriction about the motion. In this case, there's a geometric restriction relating the motion of this pulley to this mass. In the problem we just did before with the particles moving in crazy ways in space, and we did 2 particles, and we could have done 3 in an extra 5 minutes, and you're going to do it in your homework. So we can do 3, 5, 20 particles, inverse square laws, gravity, dash pots, viscous friction, quadratic friction, all those hard problems. We just write F equals ma for each particle and integrate the equations of motion for each particle. This problem, we can't do that because we have to use this extra geometric restriction as part of the problem. So that's the new hard thing here. It's not that it's crazy geometry, it's that there's this crazy new ingredient, which is constraints and restrictions. So in this methodology, the big thing is using geometry and kinematics. And I'm now sort of behind in the lectures. I don't remember whether you have homework due about this next Tuesday or not. Do you guys know? You do? Well, I think I'm going to leave it that way. The geometry, it's a big new thing. You have to get used to it, but the calculations are easy. So I'll just leave it to the textbook to teach it to you, and I'll pick it up on Tuesday, even though you have homework due Tuesday. Okay? Goodbye. Good luck.